The relationship between insulin resistance and Alzheimer's disease has grown into a central focus in neurometabolic research, so much so that some scientists have dubbed Alzheimer's type 3 diabetes. This nickname is not just provocative. It reflects mounting evidence that insulin signaling in the brain plays a critical role in maintaining cognitive function, synaptic plasticity, and neuronal survival. As insulin resistance develops in the body, typically due to poor diet, inactivity, and chronic inflammation, it may quietly begin to interfere with glucose metabolism in the brain. This disruption not only hampers neuronal energy supply but also influences how glycogen is stored and used in glial cells, possibly contributing to the cascade of damage that leads to dementia. Insulin, though commonly associated with blood sugar regulation in the body, also functions as a neuromodulator in the brain. It binds to receptors on neurons and astrocytes, influencing neurotransmitter release, memory formation, and the metabolism of glucose and glycogen. Under healthy conditions, the brain tightly regulates glucose uptake through insulin-independent and insulin-sensitive pathways. However, in the context of peripheral insulin resistance, often seen in obesity, type 2 diabetes, and metabolic syndrome, the blood-brain barrier's insulin transport capacity can be impaired. This results in decreased insulin signaling within the brain, even if peripheral insulin levels are elevated. This drop in brain insulin activity has direct consequences for how energy is handled at the cellular level. Astrocytes, the star-shaped glial cells that support and nourish neurons, store small but crucial amounts of glycogen. These glycogen reserves are called upon during periods of high demand or low glucose availability, offering a temporary buffer to fuel neuronal activity. But when insulin signaling is disrupted, the balance of glycogen storage and breakdown can go awry. Some research suggests that in insulin-resistant brains, glycogen accumulates abnormally or is inefficiently mobilized, either of which could impair neuronal support, reduce stress resilience, and increase the risk of excitotoxic damage. Moreover, insulin resistance appears to exacerbate the formation of advanced glycation end products, AGEs, molecules formed when glucose binds to proteins and lipids in a damaging, non-enzymatic reaction. AGEs are not only markers of oxidative stress, they are direct contributors to it. In the brain, their buildup is associated with inflammation, synaptic dysfunction, and the aggregation of beta amyloid and tau, two pathological proteins that define Alzheimer's disease. This means that poor glucose handling doesn't just starve neurons of fuel, it actively promotes the toxic environment in which neurons die. The link between insulin resistance and Alzheimer's becomes even clearer when looking at population studies. People with type 2 diabetes have a significantly higher risk of developing dementia, and those with even subclinical insulin resistance often show early cognitive deficits, reduced hippocampal volume, and altered brain glucose metabolism on imaging scans. These changes are not limited to the elderly. Middle-aged adults with poor metabolic health are now showing preclinical signs of neural impairment. What makes this particularly alarming is how prevalent insulin resistance has become. With global rates of metabolic syndrome skyrocketing, driven by processed food consumption, sedentary lifestyles, and chronic stress, the pool of individuals at risk for cognitive decline is growing rapidly. Yet the conversation around dementia prevention still largely ignores metabolic health as a modifiable factor. On the more hopeful side, understanding this connection opens powerful opportunities for intervention. Lifestyle strategies that improve insulin sensitivity, such as regular aerobic and resistance exercise, intermittent fasting, low glycemic diets, and improved sleep, may also slow or prevent the onset of neurodegenerative changes. Pharmacological approaches, including the use of metformin or intranasal insulin, are being explored as tools to restore insulin signaling directly in the brain. Additionally, emerging research on ketogenic therapies and ketone supplements suggests that bypassing the brain's reliance on glucose altogether may offer metabolic protection when insulin signaling fails. Ultimately, the link between insulin resistance, brain glycogen regulation, and Alzheimer's risk represents a paradigm shift in our understanding of dementia. It blurs the lines between metabolic and neurological disorders, showing us that the path to cognitive preservation may begin not just in the brain, but in the liver, muscles, fat cells, and the foods we choose every day. Ignoring this connection is no longer an option. Bridging the worlds of endocrinology and neuroscience may be the only way to truly combat the growing epidemic of cognitive decline in an aging, metabolically compromised population.